So, okay, now we have an equal number of interpreters and students. Awesome. All right, I'm going to go ahead and get started. We'll try and we'll get done early, I guess. And then I'll send out a stern email.
I have a question.
Yes.
When you get your program is not responding, is that the program or is that the operating system?
Could be either. A lot of times it's the program, and the fact that you can get program is not responding, it's isolated, so you can. But sometimes it could be the program, like waiting for something from the operating system or something like that.
Is that a deadlock?
It could be a lot of things. Like, it could be a deadlock in the sense that you, like, try and, like, say, close it or whatever, and then it sits there and hangs up, and then it times out, and then it will just say not responding. So, why it's not responding, who knows? It could be because it broke or because because there's a deadlock or something like that. But it could be either side. But usually it's the program. In most cases, if there's a problem, the program's the most likely place because the operating system gets run through more paces usually than the programs.
Right.
All right. All right, we were talking about memory management before. So, contiguous allocation. This is a I don't know about problem, but this is something that comes up with dynamic memory allocation. We were talking before about how when you can take a program and then run it, and then you need memory. So one thing is you can just pop it all into memory and start running, right? And we saw that was very simple, but it's also not very flexible. Okay. What happens more often is you'll put pieces of it in memory, and then other things will want to put pieces of their program in memory. And so what you'll end up having is little pieces of memory used, okay? And they'll be jumping around. Sometimes you'll take a piece of the memory out because it's no longer needed, and then you'll load another one in. But doing all this swapping in and swapping out, you can, starts getting hard to figure out where to place things in memory, okay? The next picture, well, first, this diagram that we see here is about just dynamic memory allocation. The idea that when you need to get at an address, you can't just give the logical address and expect the CPU to be able to access those addresses, because we've already seen that logical addresses are not the same thing as a physical address. Okay, so you need some sort of mechanism for translating that logical address into another address, and you do that by doing these base and limits. Okay, base where you say where you start counting, and then you'll go and offset, and then a limit says how far you can possibly go. Okay, because you need the base to say where to start counting physical memory that you can use, and you need the limit to make sure that you don't cross over into another part of the memory that might not be allocated. Okay, some other program might be using that. Okay, so the problem of contiguous allocation, if you look at this diagram, you'll notice that gaps start to form in the memory. Okay, in this case, we start with the first diagram, which has a larger chunk of memory assigned to process 8. Okay? Then, let's say process 8 gets done. Okay? If it's done, we no longer need to give that memory to process 8. So what do? Well, we free that memory. We free the process 8 memory. Okay? Now, after we do that, other processes will want to use that memory. Okay? So, the second picture is with the gap from process 8. The third picture here is a new process coming in. Okay? So process 9 comes in. Okay? This is starting to fill the gap. Okay? And we actually get, when the next process, process 10 comes in, we're still, have a clean fill of the memory. Okay? But in this last diagram, you'll notice that there is a gap there. Okay? If a new process comes in, it may or may not fit in that gap. Okay? So these holes in memory, okay, these are non-contiguous blocks of memory. See, when we're allocated in the first diagram, all of the memory is contiguously used. It's used one address after the other. Okay? When we get to the second picture, there's a gap. It's non-contiguous. There's a hole in the memory, and then we start using the tail end again with the process that stayed in there. Okay? This diagram doesn't show it, but you can actually get the case where, like, let's say process 9 goes away. It gets done. Okay? Then you'll have two holes, and then if another process comes in, you may have enough free memory, but you can't put it in there because there's no hole big enough for it. Okay? We'll see this is known as fragmentation, and this is a real problem with allocating memory. Okay? So just some, first of all, the terminology of a hole is just a block of available memory. Okay? And these will be scattered throughout memory depending on how processes leave and free their memory. Okay? Allocated memory from a hole large enough to accommodate it, and we need to maintain information about what's allocated and what's free. Okay? We need this free table and this allocated table to know, first of all, what memory we get back when a process gets done, and also where we can place processes when new ones come in. Okay? So, whenever a new process comes in, we have a question of where should we put it? Okay? And that diagram that they showed up there is not very good, so let me draw one. Okay? All right. So in this diagram, we have allocated and free. Okay, the diagonal lines mean it's allocated, and the blank area means it's free. Okay. First of all, how would a diagram like this? How would we arrive at a diagram like this? So which processes? Well, describe the processes that terminated.
Like what we had before, right? Maybe a big one, and then it terminated. Get two little ones, and then the first little one terminated.
Okay, so that's what has to happen. It can't be just a big process was running and then a little process ran, right? You had a big process maybe that took up the whole area right here. It terminated. Okay, so the step that you need is you need two processes to run, and then the first one quits. Okay, that's the only way you'd make the whole here, because you can't just have a big one run and then a little one run, because a little one would still be up at the top. Okay, you wouldn't have these two holes. Okay, so we have two holes now. All right. Now, when a new process arrives, okay, now we have a question of where do we place that? Okay, and there are different strategies to this. Okay, and that's what we list on this slide. Okay, are different strategies on where to put that new process that needs memory. Okay, and you'll see that there are good things and bad things about wherever you put it. Okay, first fit, allocate in the first hole that is big enough. Okay, so if you pretend like we start from, let's say this is where we start. We'll say the top of the diagram is where we start. Okay, where would first fit place this block? In the first hole, and it would fill up whatever it needed here, right? And then that's where it goes. Okay, so first fit would place it in that area. Okay? Now, best fit is allocate to the smallest hole that is big enough, must search entire list unless ordered by size, and then it has a property here. So, where would best fit place this block? Same place. So best fit would also be at the top. Okay? Notice this property. Produces the smallest leftover hole. Okay? If you take all the different free blocks that it could fit in, right? And you take the smallest one, okay, the remaining memory will be smallest for that particular hole if you allocate for this process. Okay? Worst fit, allocate to the largest hole. So where would worst fit place the block? Bottom, right? So if this is best fit, that's probably not also worst fit, right? So we have the other one. This is worst fit. And that leaves the largest possible leftover hole. Now, I don't see why they say best fit is any better than worst fit in terms of speed. First fit, why would first fit be the fastest? Right, you don't have to search the whole list. You just need to start at the top and go through and find it. And then just hit the first free block. Okay? It can get as bad as, the search can be as bad as the other one, right? Because if the list is, if the last one, if there's only like one block left, or the last block is the same as is the best or worst, no, if there's only one block left, you'd still have to search through the whole list. So, what are these two different properties? Obviously, best fit and worst fit are more interesting. Okay, one produces the smallest leftover hole. One produces the largest leftover hole. What are the trade-offs with that? Just thinking about it as far as like other processes needing memory and whatnot.
If you worst fit, then you create a larger hole, right? So you know that they'll, depending on the size of the next process, you'll probably have room for it immediately after that.
You will probably what?
Have room for it immediately after.
Okay, so if worst fit leaves the largest possible hole, that's good if the next process is how big?
Smaller than or the same size as the hole.
Okay, smaller than or the same size as the hole, and what?
The first process? Smaller? Well, I guess you don't have that for sure.
Well, if this is the largest possible hole, the worst fit is good is if you can fit in here, but you can't fit in here. Oh, I'm sorry. You can fit in the hole, in the leftover, but you can't fit in the original smaller hole. Why is that? Because if a new process comes in, first of all, let's say we did worst fit. So this is allocated. Okay? If we get a process that's bigger than the first hole, but smaller than the hole we left over, worst fit is a great choice, right? Because if the next process is, let's make this a little smaller. Okay. Let's say the next process is this big, and let's say that's bigger than this whole area, than the whole area in the first hole, okay? But it's smaller than this, okay? Worst fit is good there. Worst fit is good because we've left an area big enough to fit in the hole, okay? Whereas, it would still be big enough if we did first fit. Okay. I mean, yeah, if we did best fit. We really need two things to come in for worst fit to be better. Something else that would fill up either itself or the other hole and come in. But let me give a scenario where one works and the other doesn't. The new process is that big. A little smaller. Okay. Which strategy of the first process would allow us to run this new process next? Okay, and so first fit by coincidence, right? But best fit by design. Okay, if we do best fit on the first one, we'd be allocated up here that leaves a block big enough for the large process. Okay, so now we can allocate the large process here. If we did worst fit on the first process, this large process has to wait. Why? Because we can't fit it in the remaining block where we place the worst fit, right? And we can't fit it in the original first block. Okay? Let's see if I can get some of this a little. Design one will work better because we need a bunch of little blocks to come in. Worst fit ends up creating kind of more moderate size, more plentiful moderate size holes. Okay? What I mean by that is that you'll start taking up blocks in larger free areas. But if you're taking up a block in a larger free area, the idea is that chances are, if you're leaving a large hole, the remainder of your space can be used for something. Okay? When we do best fit here, unless we exactly match the size of the hole, we leave a tiny little gap. Right? That tiny hole, chances are, will be wasted because we won't be able to find a process that fits in there. Okay? Whereas worst fit, we leave larger holes, and then those holes can often be used because they're big enough for a process. Okay? So best fit gives us larger remaining holes, so that is good for when larger new processes come in. Okay? Because if larger processes come in and we have a bunch of small or smaller, medium-sized holes left, okay, we have to wait because we don't have enough contiguous memory to put it in, right? To put the new process in. Okay? Whereas if we have if we do worst fit, chances are we'll be able to probably use the holes that are left over more often because we're leaving larger holes and not these small ones that best fit generates. And then first fit is just by chance, right? Sometimes you pick good, sometimes you pick badly. Right? So first fit can exhibit both properties. It's just a matter of what's the order of the free blocks that are available. Okay? But the thing to really understand here is that your choice of how to place these processes in memory makes a difference as to how the overall system will perform over time. Okay? So let's take a look at some terminology regarding these kinds of holes that are left over. Okay. External fragmentation. Total memory space exists to satisfy requests but is not contiguous. Okay? So like this is like the case where we put in worst fit and then a larger process comes along. We may have a total amount of free memory that can be allocated to this large process. But we can't allocate it because of external fragmentation. In other words, the free space is broken up into blocks that make it so that no individual block is large enough to service the request. Okay? Internal fragmentation. Allocated memory may be slightly larger than requested memory. Okay? The size difference is memory internal to a partition but not being used. Okay? Internal fragmentation has to do with, this often happens if you allocate memory in blocks, where if you get to the end of a block, you kind of, chances are you'll never end directly on the end of a block. So the difference between your block and what you actually use is that internal fragmentation. You're wasting little tail ends of your memory that you're allocating. So you might have to allocate a little bit more. All right? So, first of all, the different schemes will produce different kind of patterns of fragmentation. But you can also reduce external fragmentation by compaction. Shuffle memory, to place all free memory together in one block. So, in the case of this, let's say in the case of our diagram here, okay, what would we have to do to compact this memory? Right. Well, we're going to have to move these in the middle. Right? So we can either push them up or push them down. We can optionally take the ends and also push them if we need to. But if we just want the largest contiguous block of free memory, all we have to do is we can take both of these, move that up, and move the smaller one up, and then we have the largest contiguous free block that we can have. In other words, our whole is the same size as the available memory. Okay? Obviously, this is very appealing because if the whole is as big as the amount of free memory, any process that comes in, if we have enough free memory, we can allocate it. Whereas before, we saw that there are cases where we can have enough free memory but not be able to allocate it to the process. Okay? What's the problem with that? Why?
You actually have to copy that memory into a different location.
Right. So first of all, we have to actually copy that memory into a new location. Another problem is the fact that we're changing the memory locations of everything in that program. So our memory allocation scheme, what they're saying here is also, they say it needs to have dynamic relocation. In other words, a program starts running, it might stop sometime or before it runs or whatever. We can move it to another area of memory and it will be able to handle that. Okay? Because if you move it to a new area of memory, things like jumps or referencing variables, all that stuff is broken, right? Because you've changed where it's supposed to be. Or unless there's some sort of logical addressing in there and you can just change how we map those logical addresses to physical addresses. But either way, we need to make sure that this is only an option if we can support this idea of dynamically relocating pieces of memory or used pieces of memory. Okay? And then the other big drawback is the fact that it takes time to copy memory. Even from one memory location to another. Okay? And if we don't get any larger processes that need a bigger hole than what we had, then we don't benefit, right? We only benefit if we get large enough processes that would kind of run into problems if we didn't compact. Okay? Okay. So, paging. All right. Paging is a technique, okay, where we don't deal with memory in these arbitrarily sized blocks of allocation. Okay? Paging, what you do is you divide your total memory into pieces called, guess what? Pages, right? So what you do is you divide it into pages. They actually make the distinction, and I'll make the distinction. Dividing the physical memory, you call those frames, and pages are concerned with logical memory. The reason they do that is because how we use paging because all of these schemes are ways that we can take the logical addressing of a program and put it into physical memory so that we can run. Right? So the idea is this. Paging takes physical memory and we divide it into frames. So I have 4 frames worth of physical memory. Okay? Then what you do is you take your logical addressing which may be a lot larger than your physical frames. And we divide it into pages that are the same size as the frame. Okay? Why do we do that? Because what we're going to end up doing is whenever we need to access one of these logical addresses, we take a page and put it into the frame. Got it? So the frames hold pages, and then we can, probably swap in and out of these different parts. Okay? So to run a program of size n, we need to find n free frames and load the program. Okay? So, in this case, in that example, we actually have to have enough frames to fit the program if we want to run it. Okay? So I'm going to make a smaller one. Smaller program. Okay? And let's do this. The program is that big. And I don't know if you can tell, but that is okay. So If I want to run this program, how would I do it? So I divide it into pages, and then pop the pages into the frames. Okay? So let's say all of them are free right now. So I pop this one in here, and I pop the next one in here, and it's smaller, right? But we need a whole page, right? Because we're doing everything in terms of pages. Okay? So, let's say another program comes in, and another program comes in, and it is about that big. It's about half a block, half a page. So when we run that, we'd allocate it in the next available frame, right? We make this into a page, and then we pop it into the next available frame. Okay? What's interesting about this is that if we ran another program like the first one, we wouldn't be able to run it. Right? Even though we have enough free available memory. Okay, we need actually to run, we'd actually need 2 pages, and we don't have 2 pages free. Okay? This is the other kind of fragmentation we saw, which is internal fragmentation. The reason is because we actually have to allocate a full page for any kind of, so this one that's like 1 page and a little bit, we still have to allocate the rest of its page to that program. So we only have the option of allocating in pages. Okay? But the good thing about this is that since there are these fixed sizes and we fit programs into fixed sizes, the holes will always kind of match up with what we need, because everything's expressed in terms of pages. If most of our programs, for example, are 1 page big or 1 page or less, if they're free pages, we'll have a hole big enough for it, because the holes only come in page sizes. Okay? The other thing is that this is a lot easier to track. Okay? Because since everything's on these fixed boundaries, we can deal with all of our tracking as just in terms of pages. So they show here that we can just keep track of all the free frames. We don't have to worry about the allocated pages or the allocated frames, because those are whatever's left, right? Before, with this kind of arbitrary sized allocations, we have to keep track of every start and end of free and allocated, or even just free. But like for example here, if process 9 on this diagram goes away, we need to keep track of the fact that from the start of where process 9 was till the end is free. The start of process, or of the end of process 10 to the beginning of process 2 is also free. And we have to keep track of both the start and ends of all those. Whereas with pages, we don't have a diagram. But with pages, you can just frame number 1, frame number 2, frame number 3, and that implies both the start and the end, because you're kind of divided equally in the memory.
So even if it's only 10% full,
1 page. Yeah, you have to use a whole page. Okay. So again, and then this brings up the other question: is how big should I make a page? Okay. There's trade-offs there, right? What's good about making your pages smaller? You have less wasted space, less internal fragmentation, right? You have less internal fragmentation because the difference between that little tail end that you need and the end of the page is going to be smaller if the pages are smaller, okay? But at that point, you have a lot more pages that you need to keep track of, right? And that's the main thing. Is there's a lot more pages to keep track of. I'm wondering if you get more chances are you'd get more external fragmentation as well. Probably, because you'd end up getting towards the original allocation scheme. If you make your pages 1 byte, right, you end up getting back to the point where you can allocate exactly how much you need, and then like the other scheme. Okay, so how do we deal with pages? Well, we set up a way of tracking these different blocks and what the different frames, the different pages, which pages are allocated to which frames are free. Okay, this is done using a page table. Okay, and how we generate the addresses for the CPU, because again, in any of these schemes we're trying to translate from logical addresses to physical addresses, right? So what we do is to use a logical address. First of all, you need to know where that address's page starts by giving it a page number and then an offset from the beginning of the page. So let's look at an example real quick. We'll still use this, but we'll still use the same frames. Okay, so I have frames. I have a program in there. I'll just say that. All 3 of these frames, the first 3 frames, are allocated to a program. Okay, the 3 of the program's pages are put in those frames. Okay, now if I want to get to an address, okay, what I'll do is, let's say I want to get to an address. This is the whole program outside of the frame. So if I want to get to an address here, in the middle, okay, what I need to do is I need to take the logical address that my program sees and turn it into a physical address. Okay? So how I track this is I say that this particular address is on page 2. I tell it that it's on page 2, and it is this. It's a particular amount away from the beginning of page 2. So this would be the offset. Okay? So by taking the page number 2, and the offset, I can translate this to a physical address. Okay? How do I translate to a physical address? Well, page 2 will start 1 page size after the beginning, right? Page 1. Okay? Page 1 ends at 1 page size. So we had an example before of, let's say we do 512 as our page size. Okay? So this page 2 is 512 bytes in. Okay? It's actually easier if you think about the page numbers as starting at 0. Because then you could just multiply 512 times page 1. Let's do that. I'm changing page 2 to page 1. Right? And this is page 0. The first one's page 0. So this is page 1. Page 1 times 512 would be 512. So we say 512 plus whatever the offset is. Let's say we are 25 bytes from the beginning of the page. So we say 25 bytes. Right? So our physical address would be 537. So we could go into main memory and count to 537, and we'd end up, boom, at the same spot. Okay? So 537 would kind of be what our program sees, and then we can turn that into a page and an offset, so we can just jump in at a particular page, go a little bit in, and then use it. Okay? In this case, they end up being the same. 537 is the same because our pages are nice and contiguous. So, actually, let's show it with a little bit of offset to it. Let's say now, someone ran a little program right before ours. Okay? So page 0 was allocated to another program. So when we come in, we'll be allocated 3 pages. This is our program. Okay? So now, in our program, we're still 537 bytes from the beginning of our program, right? But we're no longer starting at page 0. So, in order to translate this into the physical address, we need to see that we are allocated now on page 2 with the same amount of offset, 25, right? So now we need to make page 2 turn into bytes, which is times 512, right? Which is 1024. Add 25, 1049. We start at 0 and count up 1049. That's 512, 1024. 25 more bytes. We're at 1049. So now we again come back to the physical address. And here the physical address is different from our logical amount that we went in. So I guess technically you need to turn from the logical address into pages and then pages into... See what? Normally though, these pages are actually going to not even be in order in a modern operating system. So you have complete translation to arbitrary pages. But here we kind of take the offset, the logical address, find out what page we'd be on, and then how much into that page, and then we can go find it in physical memory. Okay? So, they are pointing out here that we have m minus n pages, where m, the logical address space is 2 to the m, and the page size is 2 to the n. So if we were 512, which is 2 to the what? Probably 9th, because 2 to the 10 would be 1024. So 2 to the 9th, okay, would be a 512 page size. We have 2 pages. So let's say we have an entire memory of 1024. Okay, we'd have 2/10. Oh, that's only 1, right? Why is it showing 1? That should be +1, I think. Okay, and then we have the offset, which can be up to, oh, that's the maximum. So 0 and 1. Okay, and the maximum would be, oh, that's not right either. What are they saying with m and n? Oh, 2 to the m minus n pages. Yes? I don't know what he's trying to say with m and n. They are related. Sorry. Okay. You have 2 to the m total address space. If you make your pages 2 to the n, right, you have 2 to the m minus n pages in that memory. Right?
So in our example,
We had 2 to the 10th
so 10
address.
9, you have
1.
page number 1 and the offset would also be.
No, you have maximum 2 to the m minus n pages. Right?
So 2.
2. You have 0 and 1.
Right.
If they're the same, If your page size is the same as your memory, you have one page. And then it goes all the way up. I don't know what they're trying to say here. Yeah, okay. So, we page a lot, okay? We do this memory allocation a lot. So often, most of these memory things that we're doing are going to be hardware assisted in some way, okay? You want them to be hardware assisted because we do this anytime we access memory, which for any program is a lot. Even just reading the instructions for the program is a lot, okay? So, the CPU wants to access a logical address. It finds a logical address in its program, right? So, what it will do is it will find out how many pages into the logical address and what offset from that page we are, where the value that we're trying to get at is. Okay? So, it will go to the page table. It will find out what frame that page is in. And now, instead of using the page number, it'll use the frame number to find the physical address. And it will use the same offset. So, the offset just goes directly into the physical address. That doesn't change. What does change is the mapping from the page to the frame. Oop, and then that will end up being a physical address. Okay? So you use the page number and offset to calculate the address, the logical address that you got from the CPU, from the instruction. Right? You find out where in the page table that page is, and it will tell you what frame it's in. And then you take the frame, use our calculation of the frame size plus the offset, and that will give you a physical address. So as an example, this CPU wants to access a logical address. So in this case, it wanted to access this logical address, the one in the example where we're at a particular, like in the middle. Okay? So you'd say, what page is that on? Well, a page is right there, a page is right there. We're on the second page. We're on page 1, if we start counting at 0. So we're on page 1, 25 bytes in. We calculate page 1, 25 bytes in. So we get that. So what we do is we take the 25, put that directly into our physical address mapping. The page 1, we decide, is stored in frame 2. Right? Times 512 plus 25. That's a physical address from the beginning to where the value is in memory.
So what exists in the page table? Is it multiple programs are in the page table?
Typically, you'll have your... we haven't really talked about what happens when you have multiple programs, but typically, each process has its own page table. Okay? Because it can only access its own pages. So this page table is, you look in the page table by looking up P, the page. And then the only value in the page table is F, the frame. Okay? So, for example, when this, in our example that I drew on the board, the program that we loaded says, okay, page 0 is in frame 1. Page 1 is in frame 2. Right? Page 3 is in, or page 2 is in frame 3. So, this guy's page table would look like this. The page table looks like the number of pages you have. 0, 1, 2. Right? Because we have 3 pages. So the page table has 3 entries, 1 for each page. And then what do we write in here? 1, 1, 2, 3. Right? Because that's how we allocated it. Do you see how this opens the door to not having the memory allocated in order? Right? Because what if I do this? I put a 0 in that page table entry. What did I just do?
The program's not in order now.
Okay, so how does the program look? By changing that number, what did I do?
Put the second page, okay, page 1 is now in frame 0.
Page 1 is now in frame 0. So what I've done is I've taken this part of the program, the middle, and clobbered this other guy out, right? And I moved it down here. I moved this middle part of the program down to the first frame. So now the program is in memory starting at frame 1, frame 1, then goes to frame 0, and then up to frame 3. Okay? And for us, that's weird, right? It's like now it's out of order. But this is still the same calculation. I mean, the middle calculation that we do to map is the same, because now, okay, what page is our target on? If we're trying to go to the same spot, this is 25 bytes in what page are we on? On what? Right? We're going in here, we're on page 1. So page is 1. Okay? And our offset is still 25. Okay? So now on page 1, offset 25. What do we do next? Go to the table. What do we look up? Page 1. Okay? So we'll look up page 1. What do we return? We return the frame, right? Frame 0. Frame 0. Offset is 25. Same. Right? 25 doesn't change ever. So, how do I turn that into a physical address? 512 times the frame is 0, right? Plus 25, which means that the physical address is 25. It works, right? This is 25 bytes in from the beginning of frame 0, right? Which is right, because if you were to take frame 0, this page that was in here, and move it up here, it would be at the same spot as before. Right? If you were to move it back up to frame 2, it'd be at the same spot as before. The only difference is that the entry we looked up in the page table gave us a different physical address.
So the page table is not really useful when everything is in order, because you just multiply.
If you even start at the beginning, and you just number and you get frame 0, frame 1, frame 2, all of these calculations didn't help you at all, because the logical address turned into the exact same physical address.
Right.
Okay? But it worked. But it still works.
Yeah.
But now, if you're offset a little, we got a neat calculation but that was very similar to just giving an offset and a base, right? Or a base and a limit, like we did before. But now we've opened the door to, now we can move stuff around. Okay? And that's even better because now we've eliminated external fragmentation. How did we eliminate external fragmentation? Right? Now, because we can make our frames hold any arbitrary page and they don't have to be in order, Now, if there are enough free pages, we can allocate you. Right? If there are enough free pages, we can allocate you no matter what the whole is, no matter what the contiguous whole is. So, for example, here's our frames again. This gets allocated to a little program . This little program gets allocated frame 1. Okay? Notice, without our little nifty page table thing, right, we can't allocate our program. Right? Why? Because we don't have a set of pages big enough to hold it. Okay? But with our nifty page table, we can allocate it. All we do is we take a couple of the pages, pop them into the free frames at the top, and then we take the last one and we pop it into the free page at the bottom. Or we put frame 0 or page 0 here in frame 0, page 1 in frame 2, page 2 in frame 3. Okay? So if we have enough pages, we can allocate it, no matter what. We just set up our page table to make sure it tracks it right. But what was the drawback of paging? So that eliminates external fragmentation. External fragmentation was you might have enough free memory, but you don't have a big enough contiguous block. So we've eliminated that by paging. But what do we take on? Internal fragmentation. Why? Because chances are, on most of these programs, we only use up some of the last page. So what ends up happening is we have all these little holes in memory. So if we make our pages small enough, we'll waste less with internal fragmentation, right? But then we have more pages to track and whatnot. And we end up getting back towards where we saw before with the we just have more pages tracked. Because before, we really didn't have the option of breaking up programs into pieces and just filling them in where we want, because we'll end up tracking too much. Okay? So, calculating a page and an offset from where you are in the logical address. We do that first. Look up in the page table to get the frame and offset, and then we can translate from the frame and offset back to a physical address. Okay? Just if you didn't see it intuitively, if I have an address like, what would this happen to be? 537 was the address. 537 was the address that we were trying to get at. Okay? To turn that into page and offset, subtract the offset. Right? That's 512. Right? Divide that by page size. Which, if it's 512, that's page 1. Okay? So, in the program, we see address 537, logical address. We subtract. Oh, we should do that reverse, right? We'll have a remainder. Because if you don't know the offset yet. Sorry. Okay. You start with the logical address 537. Okay? You do integer division using the page size. What do I mean by integer division? You basically just throw away the remainder. Or, I mean, you do division and whatever integer you get, and then you have a remainder. Okay? So 537 divided by 512 is 1, remainder what? 25, right? So our remainder is 25. 25 is the offset. And this is the page. Right? Page 1. And then that'll turn to this. You take the page, look up the frame, put the frame in the first part, offset just comes straight down, multiply the frame by 512, add the offset, and then you're back at a physical address. Sorry about that. And that's what this hardware should do. Because every time we access an address, we need to do that little calculation. But that calculation is pretty easy. So, here's an example. They have a page table that says page 0, 1, 2, 3. And they say the frames that they're in are 1, 4, 3, 7. Okay? So, the diagram shows on the right, it shows where all those pages would end up being. And notice, right, they're not next to each other. Right? Also notice that they're not in order. It doesn't matter. We do the same calculation either way. Okay? So this is all very flexible, right? It reduces the amount of things that we have to track. All we have to track is this mapping of pages to frames, right? We have eliminated the external fragmentation problem, right? And what we've generated is this internal fragmentation problem. And this is a little bit more complex than what we were doing before with just the offset and limit, or the base and limit. Right? Before we were just tracking the base and limit no matter how big our program was, right? Now we are tracking a page for every page size amount of how big we are. So, this is another view of the same thing, right? They have letters in here, right? 32-byte memory and 4-byte pages. Okay? So, 32-byte memory and 4-byte pages, that's 4 bytes is 2 to the 2, right? And 32 is 2 to the 5th, right? Okay. So, 2 to the 5th, that is 2 to the 5 minus 2 is 3. 2 to the 3rd is 8, right? Right? 2 to the 3rd is 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? We have 8 pages. Sweet. Okay? So now we have 8 pages. And then we can map by just popping in our frames again. Okay. Does everybody understand that calculation that we just did? Physical memory. Number of pages, right? So in here, 2 to the 2 is our page size. 2 to the 5. Mem size. Pages. Alright? 4, 32, 8.
So why, I don't understand why that's necessary.
What?
Where does the 8 come in?
Number of frames. That's how. to track them. That's how many frames that we'd have to keep track of.
Oh.
That's the maximum number of pages we could allocate. Right? Which is different from the maximum amount of memory that we allocate, because some of these programs, again, you can't just look at the size of all your programs and say, oh, well, I have enough to run all those. You'd have to turn all of them into pages and then see if you have enough frames. Because we're no longer concerned with, do I have enough bytes of memory to allocate to a program? Now we're concerned with, do we have enough pages to allocate to a program? Right? Whereas before in our simpler scheme,
it's only using 16 bytes.
what's that?
Only 16 bytes of it. Oh, wait. I was thinking. So the physical memory is 32 bytes.
Yes.
Okay.
So the total memory here is 32 bytes. Okay. The other thing that knowing this, like the pages and like how many pages you have, how much physical memory you have and whatnot, and the page size, that also tells you how much space you need to store these addresses. Right? If our pages, if we have 8 pages, we need 2 to the third to express 8, which means we need 3 bits. Right? So that means this, in the diagram, this F and P, those are each 3 bits wide. If our frame size is, in this case, we had a page size or frame size, which are equal, right? Our page size is 4, which is 2 squared, so it's 2 bits. So we have 3 plus 2, 5 bits. Notice that expresses the whole memory, 2 to the 5th. Right? If we have 2 to the 5th bits, we can point to any byte in memory. Okay? So think of it like this. The physical memory has to be as big as, you have to address each byte in memory. So that's 2 to the 5th. The page size or the number of pages will tell you where to draw the line as far as the bits go. Okay? Free frame list. Okay? What we saw before, the page table. We need a page table for each program. Right? Each program needs a page table so it can track where all of its pieces are. The operating system, right, or the process that's assigning the memory to processes needs a free frame list, right? Because what's going to happen is processes are going to start up and they're going to say, hey, I need 4 pages or whatever, and they'll say, can I have 4 pages? And then you go to the free frame list, you get 4 pages for the process, you give it to it, and it can fill up its page table, right? So, you have a new process in the left side of this diagram, right? It has 4 pages that it has 4 pages, and it says, hey, you got 4 frames for me. So it looks at the free frame list. It says, I have 14, 13, 18, and 20. Okay? And it says, you can have all 4 of these. The new process will populate its page table with those free frames and match them up with 4 of its pages. We'll also remove them from the free frame list, and now we have a neat little system where new processes can come to us, ask for free frames, populate their page table, start running. Okay? Just notice that our page size, our amount, compared to the amount of free memory that we have, and how big our logical address space is, all of these affect how many items we need to keep track of, right? We can make the pages smaller, reduce our internal fragmentation. We have to track more pages. We can make our pages bigger, maybe take on more internal fragmentation, but we have fewer pages to track. Okay, this relationship between those two. Page table is kept in main memory. Page table base register points to the page table. Page table length register indicates the size of the page table. Right? So what this is saying is that we have these, again, we want to take care of this in hardware. Right? So we have these registers so that the CPU can quickly access these page tables. It's kept in main memory because these can get big, too big to fit in, I don't know, custom registers on a chip or whatever. So you just keep them in main memory. And then we just have these registers that can kind of point to that section of memory and then quickly get in there and look up things in the page table so that it can map addresses. Okay? Every data instruction access requires 2 memory accesses. One for the page table and one for the data instruction. So what you do is you go in, you get your instruction, right? And you say, oh, I need to access this logical address. The logical address will do its transformation, then look in the page table, which is in main memory, get the frame, and then it can calculate the physical address in memory and then go. So notice that that's 2 accesses to memory. Why do they point that out? Accessing memory is slow, right? And this is no good. So anything that uses memory, for the most part, will take 2 accesses to memory. Okay? The 2 memory access problem can be solved using a translation look-aside buffer. Okay? Translation look-aside buffer is a type of cache. Okay? It's a cache for memory lookups. Okay? It uses what's called associative memory. Does anybody know what an associative array is? We'll start at the beginning. Everybody knows what an array is, right? Okay. What is an array? It's like a list of data, but even more than a list. What?
Where to go from one place to another?
No. What? An array it's a collection of items, but what is it? What's usually unique about arrays? Why they're not like lists?
Because you get type and
Indexed, right? So an array is a group of items, and they're often the same type. And you could say, I want item 2, so you go to array index 1. But if you say, I want index 3, you're able to get to that index and get the item from it. Whereas a list, often you traverse, right? You start somewhere and you go boop, 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 from one item to the next, right? So an array, you can get to. That was the boop, boop, boop. Yeah. Sorry. Sorry. But you do go boop, boop, boop. But yeah, in a list, you normally iterate through. Okay.
But arrays do the same thing, right? Like if you want to go to item 4, it will go to first, second, third, and it will go to 4, right?
No. Normally, since arrays are the same data, you can calculate the size of the data times the index and go directly there. In fact, like in C, for example, C will actually go through and actually calculate those as pointers. Every index is, if you have an array of ints, right, index 3 is 3 times the size of an int. That's the starting address. Whereas a list is not like that, right? A list is a pointer to the next one, which is a pointer to the next one. So you actually have to go in, grab the pointer, go, grab the pointer.
But then if you don't know where the data is, then you have to go to the whole list, right?
What do you mean? If you don't know an index?
Yeah. Like, if you don't know where the index is located, and if you need that data or something.
Yes, there are cases where you have to traverse either. Like if you're searching for an item, you have to traverse either one. Right? But lists are more flexible, but they're not as good for random access.
Yeah.
Yeah. So.
But in the case of an array, does it have to be contiguous?
Yes, it does, and that's the trade-off, right? Lists don't have to be continuous, arrays do. But throw all of that out of your memory, out of your mind, because we're actually more concerned with not the difference between lists and arrays. I'm concerned with the difference between an array and an associative array. Okay? An associative array or associative memory means that you can look up by a tag and get a value. Okay? In the case of an array, a regular array, right, the tags are index, right, and then you can go in and look up. You also may be familiar with associative arrays or associative memory as a hash table. Everyone's heard of a hash table? You take a key, you hash it, and then that will turn into some bucket where it's stored in the hash table. Okay? And then you can go in the bucket and there'll be a value in there. In our case, what do you think the tag is? In other words, the index that we're looking up by. What is it we're trying to look up? Something in the page table, right? What's stored in the page table? Frame numbers, right? How do we look up a frame number? By the page, right? So think of it like this. The tag that we're trying to look up is the page. What's in the bucket? A frame. Okay? So, the thing about associative memory, okay, is associative memory, you give it a page number and it will immediately return with whatever's in its bucket, so the frame number. Okay? Because it can actually check all of its entries at once and return based on your tag. Okay? So if I have 30 different pages in here, and they're not in order, just 30 arbitrary pages. Okay? This is a good example of your list idea, right? If we restore that in a list, how would we find a single page out of 30 arbitrary pages in a collection? We'd have to go through each one until we found the one we wanted, right? So, worst case scenario, we search through all of the items, if it's the last one. Best case scenario, it was the first one in the list. Okay? Associative memory gives you the item you're looking for in order 1, in constant time, because it'll look in all of them and return the one you're looking for. That's good, right? That's real good. If you can go in there and in constant time get the frame you want back, just by giving it a page number, no linear search through, that's good. That's super fast, right?
So that's why it's like an array.
That's why it's like, yeah, because it's indexed.
Okay.
It's actually more like a hash table, more like a associative array, where you don't have to be in order. So the restriction of an array is you have to be contiguous and the indexes have to be in order. Whereas this is kind of like that. It's indexed where you don't have to search through, but it's also in any arbitrary order. I can have index 0, index 6, index 3, whatever. I don't have to have 0, 1, 2, 3, 4, 5, 6.
How does it find it?
By searching all of them at the same time. This is hardware. This is associative memory. In the case of hash tables, you do it algorithmically, but you can still do it usually in order, constant time. The idea is that you search everything. And hash tables are usually just sparse arrays where you waste a bunch of memory. Okay? Here, we're talking about associative memory, which is a hardware implementation. Okay? So I've just told you that you can look up any arbitrary piece of information based on an arbitrary page number, and it happens in order constant time. Why don't we make all of our memory like this? That's the case, right? If you see something that's like, that has all these great properties, there has to be a drawback, right? Because you know what would be better than looking up a frame number based on a page number? You know what would be better than that? Looking up a physical address based on a logical address, right? If we can make all our memory like this, we could remap any byte into any address that we wanted and do it in constant time, which would be awesome, but it's too expensive. So what we do is we use it like a cache. Okay? So we use it like a cache so that we can use a little bit of it, of this really expensive stuff, to get better performance for everything. So the idea is, if P is in the associative register, P being the page. So if I say, hey, what frame is page X? It will either say, here's the frame number that I have in my memory, or I don't got it. If it says I don't got it, what do? We fall back on our slower method of going to main memory, looking up in the page table, and getting the frame. But what do we do then, do you think? Once we go to main memory, look up in the memory page table, right, our old, just regular old table, right? We look up in the page table and we say, okay, the frame I want to go in is 3. Okay? What should I do now? Put that into the associative memory. Put that into the translation look aside buffer, the TLB. Okay? So, if we don't find it, we put it into the TLB, probably boot something else out. Right? So what that ends up doing is giving us this nifty kind of caching mechanism where the CPU, okay, first of all, look at this diagram up here. Okay? What you should notice about this diagram is it's almost exactly the same as our previous diagram, but we've wired in this nifty little item called the TLB. Okay? This is the TLB part. We've wired it in here, here, right? In parallel with this full-blown page table. Okay, if you look back, we had the same type of thing in regular paging. Right? We popped in the TLB. So what do? I need to translate this logical address into a physical address. So I've taken the logical address, I've turned it into this format of page plus offset. Okay? Offset still just goes directly over to the physical address. That doesn't change still. But here's the trick. First, what we'll do is to get the frame number, we will send P to the TLB. Notice how they draw the diagram. They have P going into every single one of these little slots because it's doing it all in parallel. Okay? What we'll spit out is either the frame, a hit, or a miss. A miss would mean we have to go back and then follow the normal route of looking up frames, which is go to the page table, get the frame number, and pop it in. Okay? And then probably what would end up happening is the TLB would also get updated. Okay? So everybody see how this is kind of the same type of thing as like what we were talking about with caching. Right? With caching, you'd want to go to memory, you'd pull it up from memory, you'd leave it in cache so that you can access the faster memory. Okay? Before we can do any of that fancy memory access and caching, we need to do something like this, which gets us those memory addresses. Effective access time, hit ratio, is how often we find what we're looking for in the TLB. Okay? And then this epsilon for the associative lookup is saying that's the constant amount of time it takes to look up something in the associative memory. This will usually be very, very small. Okay? So what they're saying is the memory cycle is 1 microsecond. What they're doing here is they're adding up everything. Notice that when they multiply by the hit ratio, in other words, when it's in the translation look-aside buffer, in the TLB, okay, it's 1 plus epsilon. Epsilon is looking up in the TLB. We get a hit. We get the frame. Now we can look up in memory. 1, right? 1 memory cycle. Right? One memory cycle is unavoidable. We're trying to get to memory, so we need to at least have one memory cycle to go look up what we're getting. But we don't go anywhere outside of the TLB if we get a hit. If we do not get a hit, if we hit as often as alpha, how often do we not hit? 1 minus alpha. So we do 1 minus alpha, 2 plus epsilon. Greek letters? 5? 2 plus the how long it takes to look up in associative memory. So why is there 2 there?
TLB, that's 1.
No. You go to the TLB, that is...
Oh, that's epsilon. Oh, you have to
That's
go
epsilon.
back.
You have to go back to main memory to get the page from, to get the frame from the main memory page table. So that's an extra 1, and then 1 for the original memory access. So in other words, you do everything that you do when there's a hit, except you have 1 additional memory access of going to the page table. So you reduce that down, and it's 2 plus an associative memory lookup minus alpha. And that's your effective access time. In other words, this is how fast your memory will perform, which, if you get a lot of hits, makes this smaller than 2. Why are we trying to get smaller than 2? It's faster than just going to page table every time without looking up in the TLB. Okay? So, that's where we're going to stop for now. There's some stuff here, right? There's some different things that will, obviously these are types of things that we can do questions on, right? Are things like effective access time and, these paging systems are very, very powerful parts of memory management. Okay? So, I forgot my book today, so I will post up an assignment for this chapter probably tonight. It won't be due till next week. Okay? So this is kind of, before we did the midterm, I gave you a homework assignment which was just on that one chapter on deadlocks, and that was worth 10 points, and then this is going to be just on this chapter, which is another 10 points. So both of those together are like our first few assignments. Okay, because our first few assignments were on 2 chapters. So this is kind of the second half of that assignment.
Did you get it with that?
What's that?
Did you get it with
I got them. I was still waiting for some of them to get in, and I just got the last one in, so I will grade those and send them back. Some of them I've already sent back. All the ones that were before the midterm I already sent back.
This assignment we do on Tuesday?
What? The one I posted up tonight, we'll probably do next Thursday.